Hi, welcome back to my channel. Well, in this video I will try to demonstrate the analysis regarding some of the important designs which are widely used in agricultural sciences as well as in forestry, especially when we are conducting experiments in labs or in fields, and where our interest is to evaluate different objects of comparison with respect to the variables of interest, utilizing the procedure, or rather the algebraic procedure of analysis of variance. For that, I'll be using a data set which is already available on my MS Excel spreadsheet. Let me show you. The first one pertains to CRD. This is a very basic, simple data set where I will try to evaluate different treatments. I'll be using only one response variable for the sake of simplicity. The first one pertains to CRD, where I will try to evaluate 7 treatments. That is completely randomized design, not block design. The second one is randomized complete block design. I will try to evaluate 6 treatments. There are 4 applications, and the third one is Little Square design. The fourth one is Factorial RCBD. If we talk about this CRD, it is usually used whenever the experimental material is homogeneous, or we can say in context of the experiments, whenever the experiments are conducted in labs or in controlled conditions or greenhouses or mist chambers. So this kind of design is recommended. That is known as completely randomized design. This is the most flexible design, so we don't need to worry about the number of the treatments. But there might be some restrictions also, so we can use any number of treatments. But the important thing about this is that this is the most flexible designs. We can use equal as well as unequal number of replication in this design. And this is the design in which only 2 basic principles of experimental designs are used. One is replication and randomization, because the material which we are dealing is homogeneous, so we don't need to apply the third principle, that is known as local control, which is usually known as blocking. The second data set which pertains to randomized complete block design. Here I have 6 treatments and 4 which every treatment is replicated 4 times. In this design, in context of the field experiment, this design is used whenever the fertility gradient is moving in one direction. So first we need to identify its direction, we need to identify it, and it should be moving in the one direction. And then we try to incorporate the principle of local control by forming blocks which are always perpendicular to the direction of this fertility gradient. So in this design, all these 3 basic principles of experimental designs are used, including the replication, randomization, and local control. The block size in this design is equal to the number of treatments. The number of blocks are equal to the number of replicates. They are not same, only the number is same. And in this design, every treatment is replicated equally. So it's not something like in case of CRD, we can use equal or unequal number of replication. In RCBD, they are equal. Every treatment is repeated equally. So equal number of times, I can say. So the third one is Little Square designs. So this is a design whenever the treatments are arranged in rows and columns in such a way, or we can say the allocation of the treatment in the rows and columns is done in such a way. If we choose a particular treatment, it should be present in that particular row or that particular column only once. Or we can say in context of field experiments, if the fertility gradient is moving in 2 directions, then we can use this kind of a design. This is known as Little Square design. Or sometimes it is also known as row column design, because the arrangement of the treatment is done in rows and columns. And the important thing about this design is that the number of rows, number of columns, and number of treatments, they are all equal. Then factorial. So whenever we are trying to evaluate different factors simultaneously with equal precision in the same experiment, we used to apply factorial experiment. So I'll be using a data set. One factor is shade. I have 4 different levels of shade, and spacing 3 different levels of spacing, and 3 replications. And we will try to evaluate their individual as well as their combined, or rather an interaction, whether there exists an interaction between these 2 factors with respect to the variable that is biomass. So let us proceed and let us open our studio now. So for that, the first thing is I have to import this data set. So I'll be using this function, this option here, import data set. Since my data set is in Excel format, So I will click on this from Excel, then I will click on this browse. So the location of my data set is this, is the name of my data set, EOD, experimental design. I will click on this open. So this data set is imported, but here I will try to first use the first spreadsheet, that is known as CRD. So the next step is to click on this import. So this data set is imported, though there are 7 treatments, or we can say there are 28 entries, 2 columns. The first column is our objects of comparison treatment, and the response variable or the study variable in this case is yield. So the null hypothesis here will be all these treatment T1, T2, T3, T4, T5, T6 and T7, they are all equal. So there doesn't exist any kind of significant difference among these 7 treatments with respect to the variable of interest. So we need to figure it out. So in order to perform the analysis of this basic design, I'll be using a library that is known as library AgroR. This is a very wonderful library and very useful, I can say, and user friendly also. So I will press on this enter, and this is this library. You can see the description of this library. The title of this library is Experimental Statistics and Graphics for Agricultural Sciences. It is developed by Gabriel. He is the maintainer of this, and it can perform the analysis of completely randomized experimental design, randomized block design, latent square design, experiments in subdivided plot scheme in CRD or RBD, subdivided. It can perform a various number of other experiments, or we can say the factorial experiments also. So let us start with the first one. So in order to perform the analysis of this CRD, or rather RCBD or LSD also, so let us begin with the CRD. So the first thing is, whenever you are using this library, once you have imported the data set, you have to start with a default function, that is width. You can see it is evaluate an expression in the data set, then put a bracket here. Then we need to write the first thing, that is the name of data set. The name of the data set in this case is EOD. Then after that, you have to write the default function of a particular design. In AgroR, DIC is the default function for performing the analysis of CRD, that is completely randomized design. I will write DIC. Then after that, you can see you need to write again, you need to put this bracket. Then after that, what are your objects of comparison? That means the name of the treatments. Since in this case the name is, if I will show you, that is treatment. So in this, the first thing is I will write treatment, then comma, the name of the response variable or the study variable, that is yield. Then do you want to perform a post hoc analysis, or you need to figure out, you need to evaluate, since in analysis of variance or in completely randomized or any kind of a design, we used to apply analysis of variance. Once our F is significant, then we need to perform the post hoc analysis, either in terms of Duncan's multiple range test, or we need to perform analysis, post hoc analysis in terms of least significant difference. The choice is whether your experiment is planned or unplanned. So when we talk about planned, you have a control, your one treatment is control, and when you have unplanned, we don't have a control in your treatment. So it depends upon the kind of circumstance and the kind of experiment you're using. So in order to perform the post hoc analysis, you need to write a code, a default function, that is mcomp. It is used for multiple comparison tests. It will not do anything or write anything. By default, it will take two keys HSD test. But if you will mention here, I will mention that as least significant difference. Then I will try to give some labels to it. That means I will use this function ylab, which is equal to, say for example, I will write yield in kg. Then I will press enter. So within one click you can find it that a lot of information has been given by this one function. The first thing is normality of error, the second one is homogeneity of error variances, and the third one is independent of errors. Since whenever we are trying to perform the analysis of any experimental designs, the first thing is that we need to look at the assumptions which are involved in carrying the analysis of variance, and all those assumptions are involved around errors. So for that we need to find out whether our errors are normally distributed. For that, Shapiro-Wilk test is used, and it should be non-significant because its null hypothesis is that the data is normally distributed, or we can say the errors are normally distributed. So in this case we have a non-significant p-value for Shapiro-Wilk test. So it says the errors can be considered as normal. Same as the case with homogeneity of error variance, it is again non-significant. So because here null hypothesis that there is a homogeneity of error variances, so therefore the variances can be considered homogeneous. And the third one, the errors or consecutive error terms are not correlated, or we can say they are independent. And again it is non-significant, therefore the errors can be considered as independent. So all these three assumptions are fulfilled, so we are good to go. Now we have an additional information. The overall coefficient of variation of this analysis of variance in context analysis is 15.09, which is quite high. And if we talk about the general mean, we have a general this, and there are no outliers. If we talk about analysis of variance table, since the degrees of freedom in this design is t minus 1, that is 7 minus 1 is 7, and residuals are n minus t, that is it depends upon how many replications you are having in your data set. So we are having 1, 2, 3, I guess 3 or 4, that is 1, 2, 3, 4. So we have 4 times, every treatment is repeated 4 times. So the total number of observation is 7 multiplied by 4, that is 28, and 28 minus 7 is 21, so n minus t. So here you can see this p value is significant, so it is giving us a strong evidence to reject the null hypothesis that there exists a significant difference among these 7 treatments. So we are rejecting this null hypothesis that there doesn't exist a significant difference among these. So here you can see as the calculated p value, it is less than this significant level, so the hypothesis of equality of mean is rejected. Therefore at least 2 treatments differ. Then we have used this Fisher's LST, so you can see those treatment means we are having same letters, they are considered to be non-significant. If we talk about T7 and T2, there's a significant difference among these two. The same information is given by means of a very simple plot here. Since I have used this function here, I have not filled it. If I will write this function fill is equal to, and in commas I will try to write trta comma, then I will write enter. Again the same thing will happen, but this will be quite this plot will be quite different from the previous one. We'll be having a colored graph. So if we look at this plot looks quite different from the previous one because every treatment is represented by a different color, and from superscript you can conclude whether there exists a significant difference between these treatments. If we talk about the T1 and T7, the superscripts are quite different, so we can conclude they are significantly different. Rest we can conclude for others also. So let's start with another one. The second one is RCBD. I will use the same procedure. That is EOD is my data set. Then once it will get displayed here, what I have to do, I will click on this RCBD. Then after that, once it will get popped up here, I will click on this import. Okay, so we have 6 treatments and we have 4 replications and we have to evaluate them. So what we have to do in case of RCBD, we'll use the same thing, this default one with, but here after that what I have to do, I have to write the name of the data set, that I did again EOD followed by DBC. I don't need to write DIC. DI is for CRD. Then the name of the objects of comparison treatment. Then what is your blocking variable? In this case I have written it as replication, then yield, then I will write fill is equal to, in commas, trat. Then if I will give labels to this, ylab is equal to, I will write yield in kg, but here let's do another thing. mcomp is equal to lst, comma, then press enter. So here you can see what we have done. The errors are normally distributed. We have a non-significant p. Okay, there's a homogeneity of error variance, non-significant p in Bartlett's test, in Durbin Watson that is also non-significant, so they are independent, so assumptions are fulfilled. So we have a quite low value for coefficient of variation, then are not possible outliers. But the problem here is we have 6 treatments. Our p-value is not significant, it is non-significant, and since the degrees of freedom here is 6 minus 1 is 5, 4 minus 1 is 3, and 4 multiplied by 3 is 15. So we have a non-significant effect for treatments. As you can see, as the calculated value is greater than this, so H0 is not rejected, and we don't have a value for Fisher's LSD. And if you will look at the plots here, if we talk about the Fisher's LSD, they might be having the same. If I will not write it like this, suppose if I will delete this one, mcomp, if I will enter it again, you can see by default it is using Tukich HSD. By Tukich HSD, all these labels, they are same. Superscripts are same because of the fact we have a non-significant p-value for treatment. So in this case, the null hypothesis, which says that there exists a non-significant, or there is no significant difference between these objects of comparison, is not rejected because we don't have any evidence to reject it. So let us use another data set for latent square design, which is on another spreadsheet rather. That is, we'll be using the same thing, browse, then EOD, click on this open very quickly. Then after that we'll click on this LSD. Once it will get displayed here, then I will click on this import. Okay, import. So we have 4 columns, 4 rows, and 4 treatments. So what I will do for LSD, again I will start with, then after that the name of the data set, EOD, then after that DQL. DIC is for CRD, DBC is for RCBD, and DQL is for this latent square design. Then the name of the treatments, that is TRT in this case. Then after that row, then I will write column. Then after that mcomp is equal to, if I will write LSD, no problem in this case. Then fill again is equal to trat. Then after that let us give some labels to it. Yield, only yield, press enter. So default argument is missing. So what I have forgetted is that the last one is EOD, this, then I have to write yield. There's a beautiful feature about R. If you will see my previous function, the error in mean response argument response is missing. So it clearly indicates that you have not written the response variable. That is why this message, this error got reflected. So this is one of the beautiful features about R. So DQL, so again you can see DQL is the default function for latent square design. And if you will see the normality of errors, they are not non-significant. That means their existence of normality of errors. There is homogeneity of error variance also, and the errors are independently distributed also. If we talk about the treatments, only treatments are significant. These rows, they are not significant, the columns are significant. So the treatments are significant. So we have the same thing. If we talk about this treatment B, its superscript is A. A here, same is the case with this. And if we talk about treatment A, its superscript is A and A. These B and C are non-significant. But if we talk about B and A are non-significant. If we talk B and C, it is having the different superscripts. So we can conclude they are quite significantly different from each other. Let us try to demonstrate the last one, which pertains to factorial experiment. For that I will use the same thing, that is Excel. Then after that I will click here, that is browse. The same procedure, EOD, open. The only thing is that pertains to the separate sheet. I will click on this, that is FRC. Now it depends upon you. It's your choice whether you are using the separate sheets or whether you're using the separate Excel files for that. Then click on this import. So we have a data set which pertains to factorial randomized complete block design. The experiment is factorial, but the design is RCBD. So we have two factors, shade, spacing. We have replication, and we want to see their individual or their combined effect, or we can say whether there is an interaction between shading and spacing on biomass. For that, what we will do, we will use a function fat2 dbc, and you can see it is used to perform the analysis of two factors. And if I will write fat3 dbc, that is for factorial experiment where we are evaluating three factors simultaneously. So I will write dbc, then after that the name of my first factor, then name of my second factor, then my blocking variable, in this case it is replication, then the name of response variable, then I will give some captions. It is a subjective approach, whatever the units are in your study variable, biomass in kg. Then after that I need to give some legend also. Say for example I will write spacing here. Once it will get displayed, you will see what is this all about. Then let's give some, so let's suppose press enter. So you can see here we have a lot of information. The same thing, it started with the assumptions of errors. Errors are normally distributed. Okay, you can see the p-value is significant, not significant, it is quite high. Same is the case with homogeneity of error variances and non-significant p. Same is the case with independent of errors. So whether it is Shapiro test, whether it is Bartlett's test, whether it is Tobin, where all are non-significant, that means the assumptions are fulfilled. Then if we talk about the factor 1, that is equal to 3, that is 4 minus 1, that is shading. You can see we have 4 levels of shades and 3 levels of spacing. The shading is quite significant. Effect of none of the factor is also significant. The blocking is also significant. Even we have a significant interaction also. So you can see the significant interaction, analyzing the interaction. So here the good thing is you can analyze the first factor, that is shading, inside each level of this another factor. So the first factor here is shading. We can evaluate every this factor under the different levels of the another factor. So we can evaluate shade under the level of first level of spacing, second level of spacing, and third level, and in all these 3 cases it is significant. And similarly we can evaluate spacing under different levels of shading also, and it is significant. So we have a good amount of information. So this is the final table, interaction table, or we can say the two-way table. So this is quite a good information. You can see the averages which are followed by same lower cases in the column and upper case in the row. So averages which are followed in the same lower case in the column, and you can see, and uppercase in the row are different from each other as per this two keys HST, and same information is displayed here, but we need a different kind of a plot here. Let us suppose we will give a name to this whole function. Let us give some name to this function like cc is equal to, again same thing will get displayed, but the thing is that plot underscore interaction, I will write cc, so a plot will get displayed. So you can see we have different levels of shades, different level of spacing, and the same thing is that is 40.6 42 point this and 58 point this. And you can see if we talk about the shading, first level of shading, and we have different levels for spacing. The average for this is 40.6 at the first level of spacing. At the second level of spacing it is 42 point this, and you can use the interpretation, you can use this average followed by the same lower cases in the column. So in the column you have to use the smaller lower cases, and across the rows you have to use the upper cases. So a lot of information gets displayed also, and you can have additional information about the coefficient of variation, which is about 1.57, you can see, and a quite significant p-value. So this is the way you can perform the analysis of this two-way or we can say a factorial experiment with two factors. You can perform the three factor also. You can see there's a default data set which is available in this package, that is data enov. We can view this also by writing this function view enxo this. So this is the data. So we have factor first, factor second, factor third, different levels, and we have block also. Then how we can perform here, you have to use the name of the data set, then fact3 bc, factor 1, factor 2, factor 3, blocking variable response, and you can simply click on this run. You can get the information of all these things, and whether they are significant or not significant, everything will get displayed here. In this case, this interaction might not be significant in my opinion. You can see unfolding the interaction, and you can see the additional information. So a lot of information can get displayed. So if we talk about this package, let's click on this. You can see a lot of things can be done. You can perform the joint analysis of variance in context to combined randomized complete block design in case of CRD. You can perform the Pearson's correlation with interval plots. If I will click on this CORIC, you can see a lot of things. There's a default data set that is pomegranate. If I will click on this here and I will paste it here, so you can see the correlation with these intervals can get displayed. So a lot of things can be done which are commonly used in various kinds of experiments. You can perform split plot analysis also. So hope this video will be quite helpful for you, and if you want to do some another analysis, some different kind of analysis in context of field experiments or experimental designs, suppose you want to do this split plot designs or triple factorial or some other kind of designs also, you can use this library AgroR. This might be quite helpful, and this is quite user friendly and very easy to do, and at the same time you will get the results in analysis of variance, and at the same time you don't need to make separate plots for that. You don't need to do a customization for putting the superscripts on those graphs and put this different error bars. So automatically it get displayed on this. Hope you will like this video. Thank you very much.